September 1944. 30,000 feet above the Rhine Valley, Lieutenant James Howard's P-51 Mustang shuddered as he pushed the throttle past the emergency war power setting. The manifold pressure gauge climbed to 75 inches of mercury, a pressure that would have torn the engine apart just months earlier. Below him, a formation of Focke-Wulf 190s scrambled to intercept the bomber stream, but they might as well have been standing still. His Mustang accelerated past 440 miles per hour, the German fighters falling away like stones. The enemy pilots didn't understand what they were facing. They couldn't know that inside Howard's fuel tanks sloshed a chemical formula that had fundamentally rewritten the rules of aerial warfare. The story of how a transparent liquid transformed the balance of power in the skies didn't begin in a cockpit. It started in a laboratory, driven by men who understood that wars are won, not just with courage, but with chemistry. In the mid-1930s, aviation fuel across the world ran on 87-octane gasoline, adequate for the biplanes and early monoplanes of the era. The octane rating measured a fuel's resistance to premature detonation, or knock, inside an engine's cylinders. When fuel ignites before the spark plug fires, the resulting shock wave can destroy pistons, crack cylinder heads, and turn a powerful engine into scrap metal in minutes. Higher octane fuel resisted this destructive knocking, which meant engine designers could extract more power from the same displacement. Jimmy Doolittle saw the future before most. Already legendary as a racing pilot and holder of a doctorate in aeronautical engineering from MIT, Doolittle understood the relationship between fuel chemistry and aircraft performance better than perhaps anyone alive. In the early 1930s, while working for Shell Oil, he became convinced that 100-octane fuel could revolutionize aviation. The problem was economic. Producing 100-octane fuel cost 100 times more than refining 87-octane. No oil company would invest millions in refineries to produce a fuel nobody wanted. No Air Force would standardize on a fuel that didn't exist in sufficient quantities. It was a perfect deadlock. Doolittle broke the stalemate through persistence and demonstration. He convinced Shell to invest in small-scale production facilities for 100-octane fuel, then lobbied his contacts in the U.S. Army Air Corps to run performance tests. The results were transformative. Aircraft running on 100-octane fuel showed dramatic improvements in speed, climb rate, and service ceiling. In 1938, the Army Air Corps and Navy agreed to standardize on 100-octane as their fuel of choice. Suddenly, there was a market, but producing enough fuel at an affordable price required a breakthrough in refining technology. That breakthrough came from an unlikely source. Eugene Houdry, a French mechanical engineer who had emigrated to the United States, developed a catalytic cracking process that could efficiently produce high-octane gasoline from crude oil. Traditional refining methods were slow and expensive, but Houdry's process used heat and specially designed catalysts to crack heavy hydrocarbon molecules into lighter, higher-octane components. By 1938, American refineries were producing 2 million gallons of 100-octane aviation gasoline per month, with Shell alone accounting for more than 60% of production. The United States had created something unprecedented, an industrial-scale supply of fuel that would give its aircraft capabilities no other nation could match. The British initially remained skeptical. In the spring of 1940, as German forces prepared to launch their offensive in the West, Royal Air Force fighters still filled their tanks with 87-octane fuel. The Luftwaffe, meanwhile, had already transitioned to B-4 fuel with a rating of 91 to 100 octane. This gave German fighters a measurable performance edge. The Messerschmitt Bf-109E could outclimb and outrun the Spitfire Mark I and Hurricane at most altitudes. RAF pilots found themselves at a disadvantage, not because of inferior airframes or engines, but because of what flowed through their fuel lines. Personnel changes in the Air Ministry and successful tests with imported American 100-octane fuel changed minds. By June 1939, 3 months before war began, Britain started stockpiling American-produced 100-octane gasoline. When the Battle of Britain began in July 1940, every frontline Hurricane and Spitfire squadron had converted to the new fuel. The transformation was immediate and decisive. The Rolls-Royce Merlin engine that powered both the Hurricane and Spitfire had been designed to operate at a maximum boost pressure of 6 pounds per square inch using 87-octane fuel. Push beyond that limit, and detonation would destroy the engine. With 100-octane fuel, engineers could safely increase boost pressure to 12 pounds per square inch during emergency combat situations. This single change increased the Merlin II and the third engine's output from 1,030 horsepower to 1,510 horsepower. Speed jumped by 25 to 34 miles per hour across all altitudes. Rate of climb increased by 500 to 1,000 feet per minute. The Spitfire, previously inferior to the Bf-109E in several performance categories, suddenly matched or exceeded the German fighter at every altitude. Luftwaffe pilots noticed the change immediately. Fighter formations escorting bomber streams over Britain in August and September 1940 found that their previous performance advantage had vanished. British fighters they had outrun weeks earlier now caught them easily. Spitfires they had outclimbed now matched them in vertical maneuvers. The psychological impact was profound. German pilots had gone into battle confident in their aircraft's superiority. Now they fought knowing the enemy held the edge. The technical explanation was straightforward, but its implications were revolutionary. Higher octane fuel allowed higher compression ratios and greater supercharger boost without detonation. This increased manifold pressure, forcing more air into the cylinders during each intake stroke. More air meant more fuel could be burned, releasing more energy to drive the pistons. The result was more horsepower from the same basic engine design. Additionally, higher boost pressure raised the critical altitude, the height at which an engine could still produce maximum power. The Merlin was using 100-octane fuel and running at 9 pounds per square inch boost produced 1,150 horsepower at 5,500 feet. This gave RAF fighters superior performance exactly where most combat occurred, between 10,000 and 25,000 feet. Germany understood the science. Their engineers knew how to produce high-octane fuel. But Germany lacked something more fundamental: oil. The Reich possessed almost no domestic petroleum reserves. Before the war, Germany imported most of its oil. To fuel its military machine, German industry developed synthetic fuel production using the Fischer-Tropsch process. Franz Fischer and Hans Tropsch had invented this method in 1926 using catalysts to convert coal into liquid hydrocarbons. Germany had coal in abundance, and by 1936 the Brabag Company had commercialized the process. The Fischer-Tropsch plants worked, but they carried significant limitations. The process was slow, expensive, and energy-intensive. Converting coal to gasoline required enormous amounts of heat, specialized catalysts, and multiple refining stages. By World War II's peak, synthetic fuel production accounted for an estimated 9% of German fuel production and 25% of automotive fuel. 12 major factories focused exclusively on synthetic fuel production. Despite this industrial effort, Germany could never produce enough high-octane aviation fuel to match Allied output. German standard aviation fuel throughout the war remained B4, rated at 91-100 octane. They also produced limited quantities of C3 fuel at 95-120 octane. Adding C3 to B4 fuel increased the octane rating to approximately 95-130. By 1943, Germany was manufacturing small amounts of Super C3 with an octane rating of 150. But production volumes never approached German needs. The synthetic fuel plants simply couldn't produce enough high-grade fuel to supply the Luftwaffe's thousands of fighters and bombers. This disparity shaped aircraft design philosophy. German engineers, working within the constraints of available fuel, emphasized different solutions to the performance problem. The Daimler-Benz DB601 engine used in the Bf-109 employed a fluid coupling to vary supercharger speed, a mechanically complex but elegant solution to boost management. German fighters relied on larger displacement engines and water methanol injection to increase power without requiring ultra-high octane fuel. These were sophisticated engineering solutions, but they couldn't overcome the fundamental advantage Allied pilots enjoyed: the ability to safely push their engines far beyond normal limits whenever combat demanded. By late 1943, American engineers pushed the boundaries further. Testing began on fuel rated at 110-150 octane, designated as Grade 150 or PPF 44-1. The designation was somewhat misleading. The number 150 didn't represent an actual octane rating of 150, which was chemically impossible. Instead, it indicated a performance number of 150 on the rich mixture scale combined with 100 octane performance on the lean mixture scale. In practical terms, this fuel allowed even higher manifold pressures and power outputs than standard 100 octane. In January 1944, the Army Air Force's Materiel Command at Wright-Patterson Air Force Base tested Grade 150 fuel in a Lockheed P-38J Lightning, a Republic P-47D Thunderbolt, and a North American P-51B Mustang. The aircraft used in the tests were relatively early production models, not specially modified for high-performance trials. The results convinced military planners to begin immediate field distribution. Deliveries of Grade 150, fuel to 8th Air Force fighter bases in England, commenced in June 1944. The timing coincided with the intensification of deep penetration bomber escort missions into Germany. P-51D Mustangs running on Grade 150 fuel could operate at 75 inches of mercury manifold pressure. This boost level generated enough power to push the Mustang's top speed past 440 miles per hour at altitude, with some test flights recording speeds approaching 490 miles per hour. The P-51B and P-51C variants, slightly lighter than the D model, achieved similar performance gains. These speeds made American fighters fast enough to intercept even Germany's V-1 flying bombs, which cruised at approximately 400 miles per hour. The performance advantage manifested in combat in ways beyond simple speed. Faster aircraft could dictate the terms of engagement, choosing when to fight and when to disengage. A Mustang pilot who spotted enemy fighters could climb to a superior position or accelerate away from danger. If he held the altitude advantage, he could dive to attack, build enormous speed, make a firing pass, and zoom back to safety before enemy fighters could react. German pilots, flying aircraft with less powerful fuel and often facing shortages of even their standard grades, found themselves unable to counter these tactics effectively. The fuel advantage alone didn't win the air war, but it formed part of a combined Allied strategy that systematically dismantled German air power. In May 1944, the United States Strategic Air Forces initiated what became known as the Oil Campaign. The plan targeted Germany's synthetic fuel plants and the Romanian oil fields at Ploiești, which supplied much of the Axis petroleum. Intelligence analysis had identified Germany's vulnerability. Greater Germany possessed virtually no domestic oil production, relying entirely on synthetic plants and imports. Systematic destruction of these facilities would starve the Wehrmacht and Luftwaffe of fuel. Between May 1944 and May 1945, Allied bombers launched 651 attacks against German oil targets, dropping 208,566 tons of bombs. The 8th Air Force struck from England, the 15th Air Force from Italy, and RAF Bomber Command added nighttime raids. The bombing achieved devastating accuracy against specific targets. Planners used aerial reconnaissance photographs to monitor German reconstruction efforts, then launched new attacks just as damaged plants neared full production capability. This systematic approach prevented recovery. The statistical results told the story of Germany's collapse. In April 1944, before the campaign began, German synthetic plants produced 175,000 tons of aviation gasoline. By June, production had dropped to 30,000 tons. In September, it fell to 5,000 tons, a 97% reduction. Overall, fuel production plummeted from 316,000 tons per month in April to 17,000 tons in September. For a brief period from September 11th to 19th, 1944, all German refined fuel production ceased completely. The Luftwaffe had aircraft. German industry, despite relentless bombing, actually increased fighter production during the summer of 1944. Messerschmitt, Focke-Wulf, and other manufacturers delivered thousands of fighters to operational units. But those aircraft sat grounded for lack of fuel. Pilot training programs were curtailed, then canceled. New pilots received minimal flight time before being thrust into combat against Allied airmen who had hundreds of hours of experience. Veteran pilots flew sparingly, conserving fuel for emergency defensive missions. By autumn 1944, the Luftwaffe operated on approximately 10% of its minimum required aviation fuel. Interceptor units stationed to defend Germany received priority allocations, but even they faced severe shortages. Fighter formations scrambled to meet incoming bomber raids, flew one sortie, then sat idle, waiting for fuel deliveries that never came. On November 2, 1944, when the 8th and 15th Air Forces launched a massive attack, 490 Luftwaffe fighters sortied to intercept. It represented a major effort, but thousands more fighters remained grounded across Germany, their tanks empty. The combination of superior Allied fuel and German fuel poverty created a death spiral for the Luftwaffe. American and British fighters running on 100-octane and grade 150 fuel could fly longer missions, climb faster, fight at higher altitudes, and outrun enemy aircraft. German fighters, limited by lower octane fuel and chronic shortages, lost effectiveness even when they could fly. The performance gap that had appeared in 1940 when Britain adopted 100-octane fuel had widened into an unbridgeable chasm by 1944. The human cost was measured in missing faces at squadron briefings. Luftwaffe fighter pilots in 1944 and 1945 flew obsolete aircraft against superior opponents using inferior fuel, when they received fuel at all. They fought with courage, but courage couldn't overcome thermodynamics. When a Mustang running on grade 150 fuel dove from 30,000 feet, building speed past 450 miles per hour, no Focke-Wulf or Messerschmitt could follow. The German pilot could only watch his attacker vanish, knowing that if roles were reversed, his own aircraft lacked the fuel quality to attempt the same maneuver. Allied industrial capacity ensured the fuel advantage grew over time. By the end of World War II, American and British refineries were producing more than 25 million gallons of high-octane aviation fuel per day. 17 Allied refineries manufactured 100-octane and higher grades. The fuel flowed across the Atlantic in tankers, was stockpiled at bases across Britain, and filled the tanks of thousands of fighters and bombers. Logistics personnel tracked fuel as carefully as ammunition. Ground crews understood that the liquid they pumped into fuel cells was as much a weapon as the guns mounted in the wings. The chemical formula made the difference tangible. Each gallon of 100-octane fuel allowed an extra pound of boost pressure. Each pound of boost produced additional horsepower. Each additional horsepower translated to higher speed, better climb, improved maneuverability. The mathematics was simple, but the cumulative effect was overwhelming. A Spitfire Mark IX running on 100-octane fuel with monomethyl aniline additive could generate 2,000 horsepower at sea level using 25 pounds per square inch boost. The same basic Merlin engine that produced 1,030 horsepower on 87 octane fuel in 1940 now delivered nearly double that power. German chemists knew these formulas. They understood catalytic cracking, octane enhancement, and additive chemistry. Knowledge wasn't the constraint. Germany lacked the petroleum feedstock and the industrial infrastructure to implement that knowledge at scale. The synthetic fuel plants converted coal into gasoline, but the process consumed enormous energy and produced relatively low-octane fuel. Tetraethyl lead could boost octane ratings, but Germany couldn't manufacture enough of it. The C3 additive helped, but production remained limited. This wasn't a failure of German science or engineering. It was a question of resources and strategic position. The United States sat above vast petroleum reserves and possessed the world's most advanced refining industry. Britain could import American fuel across the Atlantic. Germany was landlocked in Europe, cut off from oil supplies, dependent on synthetic production, vulnerable to bombing. The Allies recognized this vulnerability and exploited it systematically. In the final months of the war, even German jets suffered from fuel poverty. The Messerschmitt Me-262, the world's first operational jet fighter, could outrun any Allied piston-engine aircraft. But it consumed fuel at an enormous rate. Luftwaffe jet units hoarded their limited fuel allocations, flying only when absolutely necessary. Many Me-262s never flew combat missions, sitting at airfields waiting for fuel deliveries that Allied bombing had made impossible. The strategic bombing campaign continued through the winter of 1944-45. Bad weather reduced bombing accuracy and allowed some German plants to resume limited production. But the cumulative damage was irreversible. Destroyed catalytic crackers couldn't be replaced. Bombed refineries lacked the spare parts for repairs. German repair crews performed heroic work, often restoring production at facilities that had been struck multiple times. But Allied planners monitored these repairs through reconnaissance photographs and scheduled new attacks timed to destroy plants just as they neared operational status. It was systematic, methodical destruction of Germany's fuel production capacity. By March 1945, German fuel production had collapsed to a fraction of minimal requirements. Panzer divisions sat immobile, their tanks empty. Luftwaffe fighters lined airfield dispersals, grounded permanently. Training flights ceased entirely. The German military still possessed thousands of aircraft, hundreds of thousands of soldiers, and substantial armored forces. But without fuel, none of it could move or fight effectively. The fuel shortage affected more than tactics. It shaped German strategic options in the war's final phase. Mobile defense required fuel for tanks and trucks. Concentrated counterattacks needed fuel to move reserves to threatened sectors. Air support for ground forces demanded fuel for fighters and ground attack aircraft. Without adequate fuel stocks, German commanders lost flexibility. Their forces became static, unable to maneuver, vulnerable to Allied offensives supported by complete air superiority. That air superiority rested on many factors: superior numbers, better pilot training, radar-directed interception, excellent aircraft design. But undergirding all of it was the transparent liquid that flowed through fuel lines and into carburetors. The chemists who developed catalytic cracking never flew combat missions. The refinery workers who produced high-octane fuel never saw battle. Yet their contribution was as essential as that of any fighter pilot. Wars are fought by soldiers, but won by industrial systems that supply those soldiers with superior tools. The P-51 Mustang achieved fame as the fighter that won the air war over Europe. Its long range allowed bomber escort deep into Germany. Its excellent handling made it deadly in dogfights. But the Mustang's performance depended fundamentally on what filled its fuel tanks. Running on 87-octane fuel, the early Allison engine Mustang was mediocre. Switched to the Merlin engine, and 100-octane fuel, and it became excellent. Add grade 150 fuel, and it became dominant. The airframe remained the same. The transformation came from chemistry. This pattern repeated across Allied air forces. The Supermarine Spitfire evolved through numerous marks, each incorporating improvements. But the jump in performance between early marks running on 87-octane and later marks using 100-octane with additives exceeded most aerodynamic refinements. The Republic P-47 Thunderbolt, already a large and powerful fighter, became genuinely formidable on grade 150 fuel. Even the Hawker Tempest and other British fighters benefited from steady improvements in fuel quality through 1944 and 1945. German pilots who survived the war spoke of the Allied fighters' uncanny speed and climb rate in combat. They described Mustangs and Thunderbolts that could accelerate away from pursuing Messerschmitts, or climb to altitudes where German fighters struggled to follow. They understood their opponents had better training and greater numbers, but they also recognized something else, a performance advantage built into the machines themselves, an edge present before the first shot was fired. That edge was octane. It was catalytic cracking and alkylation. It was tetraethyl lead and monomethyl aniline. It was industrial chemistry transformed into tactical advantage. It was the accumulated work of researchers like Eugene Houdry, advocates like Jimmy Doolittle, and thousands of anonymous refinery workers whose names never appeared in history books. Their contribution to victory was as real as any achieved by aircrew over Germany's cities. The Germans never expected high-octane fuel to turn Allied fighters into uncatchable demons. They understood octane ratings and boost pressure. They knew the theory. But knowledge and implementation are different things. The Allies had access to petroleum, refining technology, and industrial capacity to implement their knowledge at overwhelming scale. Germany had coal and brilliant chemists, but lacked the resources to compete. In war, the side with superior logistics usually prevails. In the air war over Europe, logistics meant fuel, and fuel meant octane, and octane meant victory. When the war ended, captured German aircraft were tested using Allied fuel. The results were revealing. Messerschmitt Bf-109S and Focke-Wulf FW-190s running on 100-octane and grade 150 fuel showed dramatic performance improvements, matching or exceeding Allied fighters in many categories. The German airframes were excellent. The engines were sophisticated. What they lacked was the fuel to realize their full potential. It was a bitter lesson. The best aircraft in the world is useless if you can't supply it with proper fuel. The fuel war was won in refineries in Texas and Louisiana, in tankers crossing the Atlantic, in the unglamorous work of fuel trucks and storage tanks at airfields across Britain. It was won by bombing campaigns that targeted not enemy aircraft, but the plants that produced their fuel. It was won by chemists who never fired a shot, but who gave Allied pilots the tools to dominate the sky. In the ledger of victory, those contributions deserve recognition, equal to what history traditionally grants to combatants. The men in cockpits showed courage. The men in laboratories and refineries made that courage effective. Together, they turned chemical formulas into strategic victory.